All right. Yeah. Hello, everybody. We're going to get started. There's still a line outside, but hopefully people will trickle in sooner than later. So welcome to the opening day of CCN tutorials. I'm Thomas Nasolaris, a professor of neuroscience at the Medical University of South Carolina, a member of the steering committee for CCN. This is our AI tutorial. We've scheduled 4 hours. We'll have a 30-minute break at 3. And then after this tutorial, an hour after this tutorial, we'll have a reception upstairs on the 5th floor. So it's my pleasure to introduce Danilo Rezende. Danilo studied physics at the undergraduate and master's level at the École Polytechnique in Palaiseau, France, and the Institute of Theoretical Physics in Brazil. He did his PhD in computational neuroscience at École Polytechnique Lausanne in Switzerland, and he's currently a research scientist at DeepMind. Danilo's work centers generally on the development of generative models. This is a field that's grown enormously in the past couple years, thanks in no small part to his own efforts. He's known for combining ideas from deep learning and neural networks with theories of approximate Bayesian inference, and he's published a number of really groundbreaking papers along these lines, including his paper on stochastic backpropagation in 2014. It's already been cited close to 1,000 times. And he recently authored a paper in Science on scene representation and rendering, which uses many of the techniques I believe we'll be discussing today. Very excited to learn more about that. So with my thanks on behalf of the organizing committee, I'll turn it over to Dan.
Thank you very much, Thomas. Thank you for coming, and thank you very much for inviting me. It's a great pleasure to come. Just a second. Yeah, back to business. Yeah, so this is 3.5 hours tutorial, so there's a lot of material to cover. But there's no rush. We don't have to go through everything, and at any moment in time you want to ask a question, please just interrupt me. I don't have to go through everything. I planned it in a way that makes it easy to skip parts. The most important thing is that you get some nice interaction, and you get to ask the questions that you want. Yeah, so as Thomas said, most of my work after I migrated from physics to machine learning revolves around generative models, and partly because this is a physicist bias. Before that, that's the kind of things I was already doing. It's just a different mathematical language. So in this tutorial, I organized a series of topics that I think are very relevant for the area. Okay, this is easier like this. Yeah, so this is how I organized this tutorial. So the first part doesn't have to be the first half, the first 2 hours, but as the first part, I'll go through first very basic reasons also about why do we want generative models, and what can we do with them, and hopefully I will convince the ones that are not already convinced that they are very important, that they are important. And then I go through some foundational ideas in probabilistic density estimation, and how to merge these ideas with deep learning, and how to make it work at large scale. I will pass through a broad family of generative models in details, like autoregressive models, latent variable models, and within the scope of latent variable models, which are my favorite family of models, there's a lot of things to talk about, and you don't have to understand everything I'm going to say there, or If you want to know more in details, you can just stop me and ask. So the second part, it starts with the optimization aspect of these models. How do we actually build this in practice? How do we take these models and optimize them in lots of GPUs? So this is about those optimization aspects. And then I'll dig deeper into how to make these models better. And traditionally, both in physics and in computer science, this broad variety of methods to approximate generative models was conceived mostly so that they are easy to compute things by hand. But we should not expect that a generative model that generates very complicated images to be human interpretable or human comprehensible in any plausible way. So you need approximations that are not tuned to human tractability. So, and this is where we go to more complicated ways to approximate statistical inference. So we go beyond what is called the mean field approximations to structured inference models. And I introduced a very broad class of mechanisms that we use to do very complicated inferential tasks. And then, of course, you will go through what we call today implicit models. They are more popularly known as GANs. So GANs are very popular, became really popular in the last 2 years. And I'll go through the basic ideas behind GANs, some of the principles that define a GAN, and go through why they are different from this type of models, and go through some of the main ideas that people use today to train this type of models. And to conclude, I'll go through the applications of these models to reinforcement learning, how we can transform reinforcement learning into an inference problem. Of course, these are a bunch of hammers, and I'm transforming this into some into the correct nail. And I'll conclude with the limitations of what we have currently, why they don't work the way we want yet, and what are the things that we can do next to continue the journey. So in the middle of the slides, I have these case studies, which are basically 3 papers that I have selected to talk in a little bit more detail. I don't have to go through all of them, so if there is interest, I can pick one specifically and go into details. But they are designed to clarify some practical aspects of these models. How do you build them and how do you use them in a very practical detail, so we can go in more details in these models. So why do you want generative models? In machine learning, historically, it's not that people were not doing generative models before. Generative models are there since the beginning of statistics, physics, and machine learning. But if you just think in terms, what people think when you talk about machine learning, they in general think about image classification, right? That became very popular in 2012 when a deep learning model became better than the best human handcrafted system to classify images. But there's a lot more in statistics and in computer science than classifying images. Even in the context of images, there's a lot more we can do. So of course, there's a lot of problems where there's no clear input-output. All you have is like a stream of data, or you have data that sometimes come, that sometimes is not there. And you just have a bunch of data streaming, and some parts are missing, etc. So this is not suitable for some classification system that merely takes some input and produces deterministically an output. Of course, making predictions, generative models are built in a way, the way we build generative models is by thinking how the world is going to evolve over time, or how the different variables in the real world are causally related to each other. And this is one of the key aspects of building these models, is so we can plan ahead or explore possible outcomes of some sequence of decisions we're going to take. So in the case of science, of course, and for example, finance, detecting things like surprising events, and forming more abstract representations of data. So today we have generative models already being used, like deep generative models. Of course, the generative models are everywhere. If you use Netflix, the system that proposes you which movie you're going to watch next is a generative model called the matrix factorization. You may think it's a very boring generative model, but it is one nevertheless. But you have really complicated generative models doing really cool stuff in all these areas. So scene understanding, image super resolution. So this type of model today is better than any of the handcrafted compression algorithms and super resolution algorithms that have been developed over many years. Compression of images and a representation of data in a way that supports drug discovery, astronomy, and high energy physics is a field where the generative models have an enormous growth in interest, and there is an explosion in number of papers applying GANs, VAs, autoregressive models to high energy particle physics. And there are some concrete cases where these models are helpful to find galaxies. So what is a generative model? Without going to the math, a generative model, to me, the easiest way to explain it is simply a function that transforms some noise into structured noise, uncorrelated noise into structural noise. That's a generative model. The rest, how it is instantiated, this is just a mathematical or implementation detail, but this is what it does. Mathematically, we represent the model by a probability density, which is the probability of each possible outcome of this model. And example of these distributions is for weather forecast. For example, we know that the weather forecast is probabilistic. We cannot predict it deterministically. Even if we knew to very high accuracy the initial conditions of the weather, we wouldn't be able to predict it very accurately. So even though we know what's going on is a deterministic process, it's just a time evolution of the Navier-Stokes equations, because it's a chaotic system and because there are lots of unknowns in the initial conditions, the best we can do is have a probabilistic model of what's going to happen. So there is a very nice paper that uses model for molecule optimization and protein discovery. We use they use a latent variable model to form a representation in abstract space, a smooth abstract space of proteins. And so you can do traditional optimization in this space. You know, a protein is a discrete thing that has variable length, etc. But if you encode this complicated structure into a sequence of strings, and then encode that into using a latent variable model into a fixed length vector, that becomes very convenient to do optimization. So this is what they did here. And these are, for example, samples of their generative model. So you have a generative model that samples proteins. How cool is that? So this is a recent work applied to medical data. And here, one of the most important things to me when you make a prediction is to have an idea of how variable your prediction is. And if you have just some kind of deterministic predictor, you don't have that. Here is one example. So you have this image. I think it's a slice of the lung. And this is a graders that labeled where they think a lung cancer is in this slice of image. So this is the real data. This is what the graders, the human graders, think is in this image, where the cancer is. You see there is a one grader that thinks there is no cancer there. So I want to focus only on this row for now. You see this model is looking at this image and predicting this. So it's predicting the shape of where the cancerous region is, but also whether there is cancer or not, and doing this all together in a completely joint way. And it's also giving us the variability in the shape of the region. So I think this is a very powerful thing. And this paper, I'll dig into more details in my study case 1, and I will go through some of the stats of these predictions. This is just a different data set, but the same idea. You have this image, RGB image. You probably cannot see very well from distance, but the point is like a real picture from a street, and you have labels. And these labels have been, we have erased some of the labels on purpose. So for example, there are multiple labels for person and multiple labels for car. And what we wanted to produce is a model that consistently groups all the pixels that belong to a car to either to one of the possible labels. So there's this, we created this artificial ambiguity in this data to test if the model would consistently attribute the whole car to one of the labels. So I'll go into more details why this is an improvement on what we had before. So of course, a lot of you have probably have seen this, and if you have a Google Home, you're using this. So this is a production level contribution. This is WaveNet. So WaveNet is a generative model called that belongs to a class of autoregressive models. So this is a diagram of how it generates data. It generates entry by entry in this tree-like mechanism. So it generates point by point. It's very slow, but it's very accurate. And this model, so this is just some statistics to show that this model is almost as good as a human voice. And that's why it is now at production in everything that has voice inside Google. So of course, if you follow the GAN frenzy, we like to generate images with these models, partially because it's very challenging. That's not because all the computer scientists are obsessed with images, but images are kind of the final frontier in terms of the complexity of data that we have. Although with new applications like in particle physics, we can kind of challenge this argument as they may have much more data than we can handle at this point. So this is what we can generate. This was about a year ago. This was the state of the art a year ago. And if you have been following the papers, it has improved dramatically in the last year. So another thing that is very useful, think about any real world data. You have lots of missing components like medical data, biology data. So be able to complete the missing part of the data is very important. And this is what you can do with a generative model. Because it has learned the dependency of all the variables as a whole, we can give it, let's say, in this is like some volumetric data. The model can see only half of the volume, and I'm asking it to complete the other half. So of course, this model has seen millions and millions of images like this before. And what you see in this video is a Markov chain running inside this model that generates a distribution that produces a sample of the missing part, given the part that we can see. So as you can see, this Markov chain has some kind of geometrical meaning. It produces the missing part in some kind of canonical pose and then learns to rotate it. And but this model doesn't know anything about geometry. So this image is a bunch of voxels. So it has learned this because it has millions and millions of images like this. So another thing that is quite popular in machine learning today is called what we call few-shot generalization. So few-shot generalization is the idea that I think is very common in animals and humans, that if I see only once a new object, I will immediately be able to recognize that object in a future event. So if I don't know the name of that thing, someone tells me, this is a speaker from company blah. Next time I'm gonna remember what it is. And these models, as you can imagine, they have to go through millions of images. So how can we build versions of them that can see a small number of images? So one way that is not completely satisfactory, but that kind of works, is to train it to be able to do this fast inference. The idea is that you train it, for example, on pairs of images. You say, I show it's an image of a cat, and I ask it to generate another cat differently. So it has to look at this cat and somehow absorb the essence of what it means to be a cat, so that it can generate a different cat in a different background, etc. So this is how far we've gone up to a few months ago in this idea. So this is our it's just a bunch of handwritten characters from data set made at MIT called Omniglot. So this model was trained to take one example of this character and produce random samples that look like that. So this is called one shot because once it's trained, of course, during training, it still has to see millions and millions of examples of these pairs. But once it's trained, I can show a single image and ask it to generate many different versions of the same image. And of course, you have generalizations and overfitting. All of this happen, and but you can go quite far with this simple idea. So this is the same thing, but with much more complicated images. You can see we're still quite there's still quite some way to go to get really good samples of these complicated images. But you can see that the model kind of gets what you want. It's just not capable of drawing it very accurately. So this is another really cool application. It's exactly the same type of model, but applied to functions. So basically, we are trying to learn to do what people working on Gaussian processes can already do for a long time, but we want to teach a deep generative model to imitate a Gaussian process, basically. So this has obvious advantages, but also obvious disadvantages. The first thing a person working in Gaussian process is going to notice is that a Gaussian process that can do this has one free parameter, and this model has on the order of tens of thousands of parameters. So you can imagine the amount of data, the gap in the amount of data that you need to fit this single parameter in a GP compared to the amount of data that you need to fit this model. But once it's trained, it behaves almost like a real GP with the right kind of kernel. So of course, going to predictions, this is an example of a model predicting videos of a real robot arm moving objects around. And this is our recent paper that Thomas mentioned. It's called the Neuroscience Representation and Rendering. It's basically a more advanced version of this idea of one-shot generalization. The idea of this model is that given a few static observations of a scene, it generates what the scene would look like from an arbitrary point of view. You see, this is an agent walking in this labyrinth, and this is a top view. This is what the model thinks the labyrinth looks like at every moment in time, given that it has seen this view. So as you see, when you have just a small number of views, it's very uncertain about the layout of the maze, so it's sampling like crazy, putting walls everywhere, doesn't even know the color. But as it sees more and more, it clamps more and more the uncertainty. So it would be really, really hard to handcraft a model to do this. Of course, there are handcrafted systems that can do this. It's called Islam. And an even more advanced version is called a visual Islam. But this model, it just learned to do this on its own, of course, at a huge computational price. But it works. Like, given this single observation, we can basically walk around this three-dimensional scene as if we had there. where the so as I said, another very important aspect is quantifying uncertainty. So this model, because it's a real probabilistic model, is a generative model, it can give me numbers to how much it doesn't know about the scene. So this is one example of given as it sees more and more, like here it sees nothing, so this is the amount of surprise it has when it looks at this image, is the highest level of surprise. Then it sees this image. So this image contains very little information about this held out observation here. So the amount of surprise doesn't decrease, so it's still very surprised about this image. But then we show it this second image here. The second image, now you can see the green triangle there. Then there's this massive drop in the number, in the amount of surprise of this model. It means that it learned to integrate this view and reduce the surprise of this other view. So we can quantify surprise, and as you can imagine, this relates to anomaly detection and many other things. So this is like a very quick summary of lots of papers that we've been doing at DeepMind and outside. Now I want to go through some of the technical details of these models. So as you know, the deep learning is traditionally centered around image classification. So it's a deterministic convnet that consumes an image or a video and outputs labels. So this is most of machine learning, and probably today most of machine learning is still doing that. At the same time, you have a huge amount of work in what's called probabilistic reasoning. But this work has mostly focused on very simple models, things that you can solve by hand, things that you can compute by hand, very simple models like a single Gaussian or a Gaussian mixture or a GP, etc. And now the idea is, how can we combine the two worlds? How can we put them together? So now you have seen what we can do with these models. But under the hood, what are these models trying to do? So most of these models that I've shown, I will show you some models that are not trying to do this explicitly, but these models that I have shown so far, this is what they are trying to do. They take a bunch of data collected independently. Let's say these green points here in a one-dimensional data set. And they trying to learn the density of this data point. So this is they're trying to learn this blue curve here, which is so where you have more points, they should be higher density, and where you have more spread points, it should be a broader density. But mathematically, what it means closer, and this closer is by no means a closed issue. So nobody knows what closer should mean in the case of images, for example. At least there's no agreement on what it should be. But you can describe the vast majority of all the approaches in a very simple and elegant formalism, which is, let's say you have a mathematical space of probabilities that we are interested. Let's call this space H. So, for example, in one dimension, this space is a space of smooth functions that map the real line to the positive numbers, and the norm or the integral of this function must be 1. Probabilities must sum up to 1. So this is a very simple space. Now I define what we call a probability divergence on this on this space, which is a map that takes two things in this space H and maps to R. And it must have these two properties. So it must be always positive or 0. And it's only 0 if both distributions are the same. So as you can imagine, if now you devise an algorithm that, given a bunch of points from the data and a bunch of points from the model, or the parameters of the model, can optimize somehow the parameters of the model to minimize this divergence, then the model here, denoted by Q, will approach in this sense to P. But what are these divergences? So which divergences should we use this is the thing that nobody agrees, and probably the answer is a case-by-case thing. So depending on what you want to do with the model, you're going to want different divergences. So this is examples of things that people are using now to train all these models in many different cases. I know it seems a bit messy, but there is a logic behind of all of this. It would be too much technical detail to go into the merits of each one of them. So I will just pass very quickly through this list. So all of these are divergences have a very good reason to exist. They were invented because of very specific mathematical things that people expect from probability distribution and from the type of data that are interested in modeling. So most of the models I'm going to talk today, they will be trained using these top two divergences. But at the second part, when I talk about implicit models, I'll talk more about the bottom three divergences. And one of my case studies is a model that is trained explicitly with this bottom divergence here. So the important thing to notice is that there is no single objective function that fits all use cases of a generative model. I think that's the most important message. What you want to do depends on what divergence use depends on what you want to do with the model, and it also requires a deep understanding of what these divergences will do to your model. For example, there are applications of generative models that do not care about the density at all, and when it comes to RL, this is very close to what the use case is of these generative models. So of course, if I want to do prediction, I want to be able to compute the probability distribution of future events given past events. That's the definition of prediction. But in reinforcement learning or decision systems, I want to do planning with those models. So I want to have samples from my density so that I can compute some cost over some trajectory. And I do not care if the samples are very good or they are really precise. As long as I can compute this cost correctly or is a decent approximation, that should be enough for my task. And there are lots of papers showing that these models don't have to be actually very good for RL to work or to benefit from them, which is a good thing because it's really hard to train these models. So of course, if I'm on a parameter estimation, I want to take all my data and compute the distribution of the data of the parameters given the data I have. And if I want to do experimental design, so if I'm in a biology lab or a guy at CERN thinking about what's going to be the next calorimeter in the LHC, this is what you want to do, experimental design. You want to design an experiment that will maximize the amount of information you're going to gain about the parameters of your model. This number is called expected information gain, and is what is the quantity that we use to design optimal experiments. So on practice, this is really expensive to compute, so people resort to lots of approximations when they try to use this, but that's the idea. And of course, when I want to test hypotheses, I really do not care about the joint of all my data. I care about my hypothesis. So I have hypothesis 0 and hypothesis 1, and I want to decide if one of them is better than the other. And what I really care about is the ratio. So as long as my density is good enough so that this ratio is accurate, that's all that matters. I don't have to know the joint of everything. Moreover, I can probably get a good ratio by even using a summary function that massively summarizes my data. So if you see all examples in practical physics, they are all great examples of this. When physicists decide, let's say they want to decide if the Higgs boson exists or not, they are looking at a very small number of histograms. So the data is this gazillion-dimensional vector that comes from the detector. But what the humans are looking is like 5 numbers and 5 little histograms on a screen. And they are computing the probability ratios like this. So I don't need to know the joint of everything all the time. That's the message. So To build these things, we basically have to integrate two things. So one thing is are the models themselves, which express how the data is generated, or how we think the data was generated. This is what we put in the model. But to be able to train them, we need to choose a learning principle. We have to pick one of the divergences in that table. And we have to, in practice, in many cases, we have to approximate the principle. So even the principle we want to use, we cannot use. We have to resort to some approximation to that. And oops, oh, this shouldn't happen. Okay, the point is that the final algorithm that we have is the model plus some approximation of your learning principle. And there are many places where something can go wrong. Your model can be misspecified, your approximation can be too loose, or your principle was wrongly chosen. Oh, okay. Okay, types of generative models. So as I said, for example, in the case of WaveNet, I said it was an autoregressive model. So what's an autoregressive model? An autoregressive model is simply a model where you generate things sequentially. So this is what these arrows mean. So these arrows means that I first I have some variable that I draw, let's say a Gaussian. I draw from a Gaussian Z1. And given that I have drawn that, I compute a conditional distribution of Z2 of the next variable given the ones I have drawn so far. And I keep repeating this. This is an autoregressive distribution. And WaveNet is a distribution of this type. As you can imagine, if the sequence is very long, this may be a very slow process because there are going to be lots of arrows coming. The longer this thing is, the more arrows coming to the later nodes there will be, and this is going to be quadratically slow. And this is the fate of autoregressive models is quadratic computational cost. But you can build other types of models that we call graphical models. So these factor graphs. So this type of models, you just have a set of variables, and they connect them by some function that specifies how likely the configuration of these three variables together is to happen. So this is another type of model. So this type of models are very intuitive because it's in general it's easy to think about things that are should happen at the same together or not, but it's very hard to sample from these models, and it's very hard to train these models. And if you see in terms of the history of recent history of machine learning, around 2010, between 2010 and 2015, there was a big shift from models of this type to models of this type and to models of this type. So this type, the models at the bottom are what we call the latent variable models. So these models are simply models where I first generate a bunch of latent variables and then transform them somehow, and I get my data. And what we call the prescribed model is where I have a conditional distribution of P of x given z that I know, whereas in an implicit model, well, the distribution of P of x given z is known, but is a delta. So these models have to be treated differently from this when it comes to optimization, because handling this delta function here is a very complicated thing. So just to summarize, to be clear, the difference between these two models is only what happens at the bottom. So in this model here, because of the circle, you generate x and you add a little bit of noise, uncorrelated noise in general there. And in this model, you just sample z, pass through some map, and get x. So these GANs are of this type of models, and VAs are this type of models, but you can convert this type of models easily into this type of models, but you cannot do the other way. And this is why you need lots of tricks to train implicit models and GANs. So this is just a quite short table of what kind of popular models we have now and what they are in terms of type of model and in terms of learning principle. So we have, as I said, pixel RNN and CRNN. These are autoregressive models. These are autoregressive models, and they are trained by the principle of maximum likelihood that corresponds to a particular divergence in the previous table. And which itself is an approximation for the thing that we really wanted to do, but we cannot yet, which is to be build a fully Bayesian model where all the parameters of pixel CNN would be integrated over. It's just too high dimensional to be feasible. So we have normalizing flows. I'll go through this type of model in detail. So this type of model is interesting. So it will basically start from simple distribution, let's say uniform in a box, and you apply a complicated transformation that is invertible. And because of invertibility and of some other properties of this transformation that are guaranteed, so we can compute the density at the output. And this type of model is has a new growth in relevance in the last few months in machine learning. So VAs and what we call deep Bayesian networks and even traditional Bayesian networks, they are latent variable models, not necessarily Gaussian, and they are trained by the what we call the evidence lower bound, which itself is an approximation to the maximum likelihood. So I'll go through how to compute the elbow of these models. So we have GANs, of course, and which are also Gaussian latent variables. The Gaussian part is not so important. It can be anything you want there. The important point is how you train it. This is where VAs and GANs differ, is not by what kind of models they are, but it's about how they are trained. So GANs are typically trained with different sets of divergences than a VA. And people have all kinds of arguments for this, but there's a lot of controversy, as I said, to which divergence we should use. But the nice thing about this GAN explosion is that people started discussing this a lot. So there's a huge amount of discussion and lots of papers discussing all these divergences and their properties and when they are useful, when they are not. So that is a very interesting discussion. Gaussian processes. Gaussian processes are, in principle, fully Bayesian unless you add the metaparameters like the size of the kernel, or you parameterize these kernels in some specific way. And then typically we train this metaparameters via maximum likelihood or some other approximation like the elbow, and you try to be Bayesian as much as you can. When it comes to models, a family of models called the sparse GPs or deep GPs, you have no choice but to use the elbow. And Boltzmann machines, which are kind of factor graph type of model, they are specified by some unnormalized probability density that you don't know how to sample from. So you have to approximate both the sampling procedure and the training procedure. So it makes them really hard to use in practice. So just go a little bit through the autoregressive models. So these are names of models introduced by several papers. So as you can imagine, there's lots of variants of each of these models. And this axis is basically whether they have discrete variables, continuous variable, whether they are directed or undirected. So these are models that where every variable in the joint that it defines are observed. So this is a huge spectrum of models, and these models are very useful on practice. However, when you don't observe the variables, you cannot use them, at least not easily. So as I said, you have to generate variables sequentially, and mathematically it just means that the joint of these points is a product of conditionals. And of course, in machine learning, it means every time you have something like this, you see, okay, I have to go through this bunch of nodes. Of course, I'm going to use a LSTM network that consumes the samples I have generated up to now and map somehow the state of this LSTM to a probability distribution of the next one. So this is a very popular way of building an autoregressive distribution. You have, let's say, these are categorical variables. They are integers. I sample my first integer. I pass them through my LSTM as an input. I forward the LSTM, go to the next step, sample. The LSTM at every step produces the probability of sampling each integer. I sample from that and pass the result back to the LSTM and so on. So a popular way of doing this for images is to scan the images like this. I generated this pixel, and then I moved to the right, I generated the pixel on the right, and I generated the whole row like this. Then when it comes to the next row, of course, I can only use the pixels up to the point I have sampled so far, otherwise I would have some kind of acausal model of the pixels. So this kind of model works surprisingly well for images. Okay, latent variable models. And I just emphasize again, so if you have any questions, please interrupt me, or if something I say is not clear, just ask. So latent variable models, there is a lot of latent variable models in statistics, computer science, machine learning literature. You can split them into discrete, non-parametric, continuous, directed, parametric, non-parametric. So there is a lot to read in this field. So, but basically what it is a model of this type. It means that there is some variable z that I do not see in my data. So my data is a bunch of variables x. So I do not see the variable z. For example, let's say my data is this image, and the z variables are the positions of all the objects in this image. I do not see the position of the objects on the image. I just see a bunch of pixels. And for example, if there's occlusion, I cannot even map the pixels back to the z's of the object that is occluded. And maybe I don't even see an object that's entirely occluded. So the z's that would describe this image that I'm seeing like right now, which are the positions and orientations and the colors of all the objects, is a massively under-observed variable. And the idea here is that the data was generated in a way where you have the parameters, which are fixed, you sample once and keep them, and then for every prediction you pick a new z and generate a new x. So mathematically this means that the density looks like this. Oops. And so this is just a very simple instantiation where all these things are Gaussian. This is just to put precise names on the things, like this distribution over z is a Gaussian. I put some Gaussian on theta, and this conditional is a Gaussian. Everything is a Gaussian. As you can imagine, Gaussian is a very useful distribution. But if you could marginalize theta and z, this model wouldn't be a Gaussian anymore, which is interesting. But the point is that you can easily build this type of models. So this is just another way to represent the same thing. So I can say that instead of having a conditional distribution here, I can write exactly the same thing as a deterministic map. So in this way of looking at the model, I build the p of x given theta and z, and in this way I have just a deterministic function that creates these deterministic nodes that I just pass through and go back to x. So this change in a way of looking at exactly the same thing was very helpful to merge deep learning and the generative models. Why? Because now these things are nodes in a graph and that are deterministic. So this is essentially now a neural net. So you can transform your Bayesian net into a neural net. And you cannot put a bunch of distribution nodes in TensorFlow, but you can put functions in TensorFlow. That's another point. Now, latent variables. So what makes it really harder to train is because now, let's say this model here. You have these multiple latent variables that conspire to produce my data. Now, given an image X, there are many, many different configurations of the latent variables that would have generated the same X. And this is what makes it hard, because training, as I'm going to show, requires that I invert the generative process. So I have to compute the distribution of Z given X, and this is a very hard process. So that's where we have to approximate the principle of learning. So we want to train this by maximum likelihood or integrate out of the parameters, but the point is we cannot on practice. So you have to approximate, and these approximations are tricky, and a lot of the things that made us capable of training this at a large scale in many machines and in big data, in big images, is the machinery to do this this inversion. So now we have all these types of models, and this is just a summary of kind of algorithms that exist to do this inference, to do this inversion. So in the models of this type, we can have many algorithms to approximate the distribution of z given x. And for models of this form, we can do some of the same techniques, but some of the techniques do not work. So you see there's some mismatch between the list of things we can do here in the implicit model side and what you can do on the prescribed model side. And hopefully one day there will be no difference between them. We'll be able to seamlessly go from one to the other in both directions. Now, this inversion process, which we call the inference, so this inversion process is the thing that I want to compute now, or approximate. And this algorithm that we call the stochastic backpropagation and its variants are basically efforts to approximate this process in a way that we can scale. So the idea is that let's consider the type of model of this form. So it means that you have a distribution of latent variables, let's say Gaussian or uniform, and given a sample z, I generate an x from another conditional distribution that has some parameters. So I have a bunch of data points x, and I want to maximize the likelihood of these data points. So I have already given up integrate the parameters because there are too many of them. So I won't even bother trying to put the parameters into the formula. So I want to find a way of approximating this quantity so I can maximize it, basically. That's the goal. Approximate this so I can compute its gradient and climb it. So if you write the log likelihood of the whole data set, it is just a sum because the data points are independent of each other. And now, of course, as anything that is, any task that is useful and hard, there is an immense array of algorithms to do this. I'll go through some of them called Laplace approximations, importance sampling, and then the variational approximation. I will very quickly pass through what we call perturbative correction, and there are many, many other methods that I will not even pass through in the literature to do this. So the idea of Laplace approximation, oops, this figure should be after the thing. Okay, so I want to approximate this expectation. So this expectation, you see, look at what's going on here. So I have a log of an integral, and I want to be able to compute the gradients of this thing with respect to the parameters theta. So if I just naively try to compute the gradient, what's going to happen is that the gradient will pass through the log, and I have some nonlinear function of this integral, which is an expectation, inside my gradient. And there is no way in general to have a unbiased gradient estimator of this type of problem. So to be able to build a unbiased gradient estimator, we must somehow put the log inside. Yes? Yeah, that's a very good point. So an unbiased estimator means that on average, the gradient will point to the same direction to the true gradient. So I'm going to create an algorithm that works on samples. So at every training iteration, I'll draw some samples from the data, and I'll draw some samples from Z. And there is a function that is going to take that and output my gradient. And I want that on average, this function returns the true gradient. So this is what means unbiased the gradient estimator. At least it's not entirely necessary to be unbiased. There are trade-offs. You can do the famous trade-off bias variance. So you can accept some bias if that massively reduces the variance of the estimator. But this is hard in such a general context. So we want to get the bias out of the way so you can think about variance after. So I can rewrite this this formula like this. I just put this in the log. So this u is just the log of what was there. Now the idea of this approximation is to say, okay, this u, it will have some shape, but most of the mass is going to be around the peak of this density. Let's say there is multiple bumps like this. If I truncate this density here, you see that most of the mass is going to be under this big bump, and another big fraction of the mass is going to be there. I mean, by mass, I mean the how much of this integral lives under this chunk of the function, and how much of this integral lives there. So the idea of this approximation is to say, okay, I don't know how to compute this integral, but I'm going to say that this u function looks like a parabola around the peak. So I'm going to do a quadratic approximation of u around the maximum point. So at the maximum point, I compute the gradient, which is 0, because it's the maximum, is the local maximum, and I compute the Hessian matrix. Now, if I do this approximation, I assume that this function u is a quadratic function of z now, around some point mu, in this case, in this one-dimensional example. Then I can solve the integral because it's just a Gaussian now. I transformed something very nonlinear, I did the quadratic expansion, and now it looks like a Gaussian. So because it's a Gaussian, we can solve the integral, and we have that the log probability that I wanted now, I have a closed formula for this. So this is the Laplace approximation. Of course, as you can imagine, I choose this example on purpose so that it's a bad approximation. It's bad approximation, why? Because we have multiple peaks. So if I approximate the function around one of the peaks, I'm gonna lose a lot of this integral. So the goal, I want to integrate this blue thing here, but I'm saying that this blue thing looks like the yellow thing. So of course, this is not a good approximation in this case, but if the blue thing was just some kind of bump, the shape of this density looks of this u function looks like just a bump. This would be a good approximation, and in fact, a lot of approximations in physics are based on this formula. Yes, yes, please. Yeah, no, you have to choose mu, and what you have to now, if you want to choose optimize, you have to do an alternating gradient descent. You find mu first, then you fix it, and then you optimize the parameters, and then you recompute this again, and then you optimize the parameters. And this optimizing the model with this approximation is quite expensive because you have this Hessian. You have to compute the gradients of the determinant of the Hessian, which is cubic in the number of things inside. So this is a closed form approximation, but it's still expensive. So in some cases, this thing you can compute by hand, and then you can compute its gradient. That's fine, but if you have a complicated model, this will not buy you much, even though you have massively approximated your model. So please stop me if you have more questions. Sometimes the notation is not completely consistent. So another way of approximating that is more generic, but everything that is generic comes at a price of a higher variance, but at least you can apply to a broad variety of problems. It's called importance sampling. The idea is the same integral as before, and I rewrite it by multiplying. So this is an expectation under this P of z. So I multiply the thing inside by Q of z and divide by Q of z. So I didn't change anything. I just multiply divided by the same thing. Then I rewrite it as an expectation under the Q of z. So this Q of Z now, in this context, is called the proposal distribution. And this ratio, probability ratio here, is called the importance weight. So mechanistically, what happens is that I want to compute the expectation under P of Z, but I invent some other distribution, Q of Z, and I'm going to use that to compute the original expectation. And of course, I cannot just sample from that and put on the expectation, because this distribution is not the same as this, and it's going to create a bias. So to correct for the bias, I have to reweight the samples according to how likely they were under the original distribution. Then I can rewrite the thing inside, using the same trick as in the other slide. I just put everything inside the log, and I call it F. So in this called F. This F comes from free energy in physics, because this F looks like some energy, potential energy minus entropy, if you look at the terms inside. So that's why we call it free energy. But in this context, it has nothing to do with real thermodynamic free energy. So I'm just rewriting this thing now in a different way. So instead of taking the exact expectation, which we can never do in practice, I'm going to sample k times and build my estimator. So this log k is just because this was an average and I wrote as a sum. So I took the log away. So now this estimator, it has a nice property, which is that on average, it is a bound to the true thing that I want to optimize. So now think about it. I want to maximize this number, log p of x, the likelihood of my data, which is the original thing. I want to maximize it. But what I have now is a lower bound on average. So it means that it's okay for me to try to maximize my lower bound, because maximizing a lower bound, provided that the bound is tight enough, is eventually going to force the true likelihood to start going up. Unless your bound is so loose that maximizing this is so far from the original thing that nothing will happen there. And this can happen in practice too. So, but this is the importance sampling estimator. And its gradients are biased by the same reason as I mentioned before. You have a log of a sum. Every time you have some nonlinear function of an expectation, it's going to be really hard to produce an unbiased estimator of this quantity. Unless you know a lot about the behavior of this expectation, then so that you can remove the bias with some statistical tricks. But in general, that's not possible. So this estimator is biased, unlike the previous estimator. But at least it has one knob, which is this k. And by growing k, I can make it more and more accurate. So if I make k very large, this quantity will saturate, and this will be the true likelihood. Of course, it comes to the price. It's expensive. So for each k, I have to compute this function inside. So I have to take into account how much compute I want to expand to approximate my objective function. So, and this is one very simple example. Let's say your distribution looks like this blue curve, which comes from a generative model that I wrote here by hand. I just made this on Mathematica. This is the joint, x and z. Now, this is the p of x comma z. So if I want to compute p of x, I have to integrate or basically sum the rows of this matrix. And this is the blue curve. Now I computed the importance sampling estimator for a different number of samples, and this is the dashed curve. So you see that if I use a small number of samples, like 600, the bound is so bad that you don't even see that it has the same structure as the real density. So now if you try to optimize this orange thing at the bottom, you'll probably not learn anything. Now, as you go number of samples, the bound gets closer and closer to the true thing. And you can see the number of samples is very large here compared to how complicated this thing is. Yes, sure. Yes. Yeah, so so the importance sampling estimator is a biased estimator. I can control the bias by growing k, so I can prove that the bias go to 0. Yeah, exactly. I have this knob. The two things happen as I grow k. This whole thing gets closer and closer to log p of x, and the bias go to 0. But in practice, there's a problem. It goes too slowly to 0, and that's a lot. That's why this method is really hard in very high dimensions, because as you grow the dimensionality of the space, the number of samples you need to reduce to have the same amount of variance must grow very fast, and this is the typical challenge of this approach. So now, the idea of variational inference. So again, our old integral, the same quantity as for all the other cases. I will do the same trick as the importance sampling trick. I multiply and divide by some q of z, by some proposed distribution. But instead of keeping the log outside, I'll just put the log inside. This may look like some bad math, but it's actually, you can prove, and it's called the Jensen bound, that if you put the log inside, for any q, you have this inequality. And moreover, you can prove that this inequality will be saturated when q of z becomes equal to the posterior. So this inequality will be saturated when q of z is equal to p of z given x. So now, if I write, just put this back into the main formula there, I have this bound, which is called the variational bound. And this bound is also in the right direction, because I want to maximize this number, and this is a lower bound. So if I had upper bound here, this would be catastrophic, because if you're trying to maximize an upper bound of something, two things can happen. The original quantity can go up, or the gap between your approximation and the original quantity can go up. So it's not guaranteed that it is, if this bound was in the other direction, optimizing this quantity would not be guaranteed to improve the model. Now, I don't have to spend too much time on this, but on this idea, but it's similar to this idea of the, yeah? So, yeah, sure. Yeah, no, this is a different one, because the log is inside there. The log is on the other side, but you would get this lower bound by using a single sample, as k equals 1. So if you set k equals 1 in the importance sampling, you get this bound. However, the difference now is that this thing, the whole point of this is that even though it corresponds to the importance sampling with k equals 1, by optimizing q, I can make this bound tighter and tighter and tighter, instead of relying on growing the amount of parameters, or amount of computation. I will rely now on optimizing a distribution queue. Of course, if I have a good queue, I can also use it to do importance sampling, and that's what people are using now. So you have this feedback loop among approximations. If you have a good queue, it also happens to be a good proposal, because you can prove mathematically that the queue that reduces the variance of this is the posterior. So the posterior distribution is the proposal distribution that will create the lowest variance. So even if you're not trying to compute the posterior, it will come out of math, just to try to do the right thing. So the idea of perturbative approximation is similar to the quadratic approximation, but the difference is that you just keep going on the polynomial expansion. So I'll not go much in detail. So if you have seen or you know about Feynman diagrams in particle physics, Feynman diagrams are a way of computing perturbative expansion for some particular generative models that appear in physics. So Now let's look a bit at different terms in the variational bound. So that we can split into two terms this thing inside. So we can split into a term which we call the reconstruction term, the reconstruction error, and the regularization term. The reconstruction term, we call it this way because look at what it's trying to do. So we will try to maximize this thing. So if you only look at this term, what means maximizing this? It means that I have to produce a z for a data point xi. So the Q knows I. So it, for each data point x, it must produce a distribution of z such that when I condition p of x on that z, it will have a high likelihood again. So imagine that this p of theta is a simple thing, like it's a Gaussian. So if this p of theta is a Gaussian with a mean that is a function of z, it means that I have to basically recreate x from z. So that's why we call a reconstruction. And this term, it is what it is doing is that it is a regularizer that's called the KL divergence, which is one of the divergences in the table I showed before, which penalizes the Q, this distribution Q, from deviating too much from the prior distribution, PZ. So basically, now we have these two things fighting against each other. This is the energy term and the entropy term. And they are fighting against each other. Because as you can imagine, for example, the best thing to do for this term would be to just, so this Q would become just a delta concentrated at the point where this thing is maximum. This is what would happen if you ignore this term. But, if you train these things, you see that Q will concentrate and go towards a very concentrated density, but then at some point this term will kick in. It will prevent it from concentrating more because it is trying to pull this distribution to look like the prior. Let's say if your prior is a 0,1 Gaussian, this term is trying to make the posterior look like a 0,1 Gaussian. But of course, if it you sample from 0,1 Gaussian, you cannot reconstruct. So these two things are fighting against each other. Yeah, so as we have seen, so there are many choices of models that you can use. This P of x given z can be many things. Can be given simulators. For example, if you're trying to model weather, this P of x given z will have the Navier-Stokes equations inside that simulates how the air moves around. And if it's your generated images, you could imagine a P of x given z that has a render engine inside, and z is a list of position of stuff and their textures, the position of light, etc., etc., and the P of x given z would generate an image. And there are many examples you can imagine like this. So we've passed through the variational optimization idea, and I didn't speak so much about this, but so thanks for the questions. So everything we do here is based on a set of samples. So I draw a batch of samples from the data, let's say 100 samples from the data. For each data point, I will sample these latent variables, and I will estimate the gradient of this quantity, and I will optimize. So this is what we call the stochastic variational EM. So this algorithm already exists long time ago. All we are doing here is replacing very simple linear relationships by deep neural nets or convnets, so you can model very complicated data. So this is the idea of the variational EM algorithm. So for each data point, so it's a two-step algorithm. That's how it's traditionally used. At the E step, at the expectation step, we compute this expectation and saturate it. And we set the posterior to the Q that saturates the bound. They get the bound as tight as possible. So the E step, I try to make my variational approximation as good as possible. I tie the gap between the true distribution and the variational approximation. Then at the E step, at the M step, I optimize my parameters, and then I alternate. So this is you can use this if you want to train a Gaussian mixture, for example. It's just that in a Gaussian mixture, for example, if you don't have any complicated priors, you can compute all of these steps in closed form. So you don't have to do separated optimization loops for that. And you can write, if you write, think in terms of a computational graph, what you have is that you have this object that's called the E object, that it takes as input the joint between X and Z. It takes a variational approximator with some parameters. And what it gives as the output is the gradient of the bound with respect to the parameters of the variational posterior and with the respect to the parameters. And on practice, we basically, this is the stochastic backprop machinery happens inside of this box. So you can basically optimize everybody jointly. And I'll go expand this a bit more. Now there is still a problem with this, which is this index here. So if I have yes? Yes. Yes, if Q is the true posterior of Z, then we get exactly N. Yes, yeah. Stochastic VEN, yes. And there is a double stochasticity here because you can also do the optimization for theta in a mini batch instead of, so you have the another stochastic, there is a, that's why some people call this double stochastic EM or variational approximation. So one limitation of the thing I described so far is that you're going to encounter, as soon as you try to apply this to a very large data set, is that this Q has this index, right? This I is labeling the data. So if you have 1,000,000 data points, you need 1,000,000 Q of Z. And of course, that's not feasible in a very large problem. In some problems, it does work, and that's what you do, and that's how people have been training large Gaussian mixtures or Bayesian networks, etc., for many years, and it works. However, if each X is an image and this Q of Z is a distribution over thousands and thousands and actually tens of thousands of Z, this becomes much less tractable. The amount of memory you need becomes untractable. So the idea here is to instead of just having a list of posteriors of Q of Z, I have a parametric family of distributions that are conditioned on X. So I create some parametric family of distributions. Let's say, for example, Q of Z is a Gaussian where the mean is a function of X with parameters theta, with parameters phi, for example. The mean and the variance are functions of X with some parameters phi. And now what happens is that I converted two things happen. Now I don't have to store Q of Z for each data point anymore because I can recompute it on the fly. For each X, I just compute this conditional and sample from it. So I don't have to store the value anymore. I can compute on the fly. I'm trading memory by computation. But another thing that happened, which is also very useful in practice, is that now the argmax before was over Q. Q is belongs to a set of functions, so it's very hard to optimize a set of functions. And this is what actually gave name to this problem as variational inference, because variational method is a method where you optimize over functions. That's what means variational. So variational has nothing to do with this particular way of doing. Variational just means optimizing over functions. So we actually converted the variational problem into an optimization problem, because now the argmax is over a finite number of parameters. So this is a very useful in practice. So now it comes to the model that we call VA. So VAE is the simplest instantiation of these ideas together. So we build a prior over Z. We have a decoder that takes Z and produces some X, and they create an inference network that is a neural net that takes X and parameterizes a distribution of latent variables. And this is one way of expressing that. I have a posterior sample, let's say a Gaussian, with some sufficient statistics eta that I compute from the data using some parameters. And then we just optimize this loss. And now, by just optimizing, I mean you sample data points X from the data, then for each X you sample one Z, and then you just you compute a very cheap unbiased gradient estimator of this quantity, which is the next, which is going to be the next part. So let me just summarize the things that I've shown up to now. So I've gone through some applications of generative models, why I think they are very useful. I've gone through the idea that allow us to go back and forth from graphical model representation of a distribution and a computational graph representation of a distribution, which is just noise going through deterministic nodes, instead of seeing a distribution as a bunch of conditional densities. We investigate different types of generative models, autoregressive, latent variables, and we talk about the variational principles, variational approximation, and about the idea of amortized inference, which is this shift from having one posterior per data point to have a conditional posterior that I can compute on the fly. There's one thing I didn't mention about this. Another advantage is at test time. So let's say now I give you a new test image. This is not in your training set. If you do a variational inference in the traditional way, you would still have to solve an optimization problem to compute the likelihood of a test image, because you don't know the posterior. You have computed only for the training points. So for any new test point, you would have to solve an optimization loop until convergence to get the posterior. But if you trained a posterior that is parametric and takes any X as input, at test time, all you have to do is just pass your test data there. Of course, this also has drawbacks. For example, Q of Z given X may overfit. So the same way as the generative model can overfit by memorizing the data, the Q of the posterior can overfit by only being capable of computing the posterior of the training data points. And this happens in practice, and there's papers showing that this happens in all kinds of settings too. So there's no magic. So if everything is about doing trade-offs, right? So before we had a posterior for each data point, we know that there was no trade-off in terms of the complexity of the data and the quality of the posterior. There are disjoint things. But now, because my neural net has to map X to Z, it has to be as complicated as it has to be for this map. So imagine that your generative model is a render engine. So as input, it takes a list of objects and outputs an image. And the list of objects are your latent variables. What Q of Z has to do is has to look at image and output a list of objects. And this is incredibly hard. So this Q of Z has to solve a very hard problem. But at least now we have an algorithm that is very cheap to approximate, and I'll go through the actual gradients in the next bunch of slides. And we know they're unbiased gradients, and because the computational cost now is everything is the same cost as the backprop through the joint graph of the generator and the encoder, so and the cost of backprop is linear in the number of parameters, it has a very nice scaling capability. Yes? Yeah, exactly. In this example, there would be no free parameters in the generative model, or maybe there are some parameters like the set of textures you're going to use, and then Q, you have to, you don't specify which texture is there, you just pick one of them, and then let's say the color of the texture must be learned, for example. You can imagine all kinds of intermediate like blends between a completely learned map from latent to image and something like a render engine that has no, almost no free parameters. Exactly. So if it's not differentiable, this algorithm, and I mean the algorithm, the next page, which is the backprop through this graph, wouldn't work. So we have to use other types of approximations that I will not go in a lot of detail, but I will just quickly pass through them. But it's also possible to estimate the gradients even if the render engine is not differentiable, the P of the map from Z to X. But that's not easy. And the general purpose algorithm that we have is a very high variance. So it's very general, but a very high variance, so which is called the likelihood ratio method. So you have all these trade-offs. The likelihood ratio method you could use for any model, but it's very high variance. And because here I know the gradients, and even if I really wanted, I even know the Hessian of this thing, I could even use that to optimize, to reduce variance. So for this type of model where everything is smooth and differentiable, there's a likelihood ratio method. It simply does not compete with this gradient estimators where everything is smooth. But if you have no differentiable parts, then you have no choice. You have to use some algorithm like this. So I don't know if anyone has some questions about the other about the previous slides, or something that they want to clarify. So I have one case study, which is one paper. Let me just check the time. So I have 30 minutes to the break, and I'm gonna. So this case study is quite short. So is a neat example that you don't have to do something complicated to be useful. So the idea of this paper was to do a probabilistic segmentation of medical images. So let me see here. So as I said, you have these images of slices of 3D images of lungs, of human lung, and you have these human annotated cancer labels. So the human annotator, it goes pixel by pixel, say this is cancer, this is not cancer, this is cancer, this is not cancer. And then it builds, they make this image. So here is you have 3 human annotators for the same image. So this data set, it's called LIDC, and I don't remember how large it is, but it's not very large. And for each slice scan, you have 4 human annotated images like this. So this model is like a VAE type of model. It has a particular architecture that we call a UNet that was introduced exactly for this type of problem before. So the UNet is called the UNet just because of this the way you draw it. It looks like a U, the U symbol. And the idea is that these are all convolutions. And the goal of having such architecture is that you want to take the image. So these images are very large. They are medical images. So for this whole thing to be useful, you have to be able to handle the real thing. So the real image. So these images are like 1,000 by 1,000. So there's not much you can do here that would fit in a machine, in a single computer. That's a big challenge here. So that's why at training time you train on much smaller patches, like 200 by 200 or 500 by 500, but the real images are much larger. The point here is that we want to map this RGB image, this grayscale image, to the label, and we want to do it in a way that preserves the spatial structure. So we use a convnet that looks at the image very locally and copies the. And it has a very local computation shortcut here. So this is our local computation convnets. And every time I shrink, we shrink the size of the layer. We create a more global. We have the chance to do more global computation of the images. And this architecture is very good without even making it a generative model. It is very good at this task. So it's before this work, it was the state of the art at doing this job. And what we did, we transformed that into a VA, convolutional VA that has this UNet architecture inside. So now, to make it into a VA, we basically, from the image, we compute a prior, which is just another convnet that parameterizes a Gaussian. And this works in a very low dimensional space, like a 2 or 3 dimensional, because we want to interpret this latent space. We want it to be interpretable. So, and then to make predictions with this model, what we do is that we take the scan image, build the prior, sample from the prior, and combine the prior with the input coming from the scan image, and that generates a sample from the image. And during training, this is how the computational graph looks in TensorFlow on the computer. You have to compute. You have to compute the inference network as well, the posterior network, which is this network here, which is just on real instantiation of the model. Is just a convnet that takes both the target, the ground truth, and the input image, and computes the posterior, which is just a Gaussian in this case too. So it's a very simple VA. So this architecture is really simple to implement with modern tools that we have now in deep learning. So this is the loss, as I said before. So this Y is are the labels for each pixel. This S is just this map that takes the ground truth image and input image to the latent, to the parameters, to the probabilities of each pixel being of each label. And you have the KL term. This beta thing you can ignore for now. So this is just to compare to previous things that people tried. This is just the UNet alone. This thing just on its own, it does a good job. But of course, if this is a deterministic model, it cannot give alternative labels. It is a deterministic thing, so it's not going to give us uncertainty estimation. And before, what people did in the field of medical image segmentation, so there are many solutions to this problem in other areas of machine learning, but for some reason there was some kind of weak communication in the case of medical image labeling. And people invented some weird algorithms there to try to come up with this. And so one algorithm there is just you train this UNet, but then you retrain the n heads of the model on resampled data, as like some kind of resampling technique for the data. And this is just to train m independent models. You just resample the data m times and retrain everything independently. And in this case, in this model, you have you add something to the loss to encourage these different heads to be different from each other. But it's a kind of heuristic. And in this work, we just define by construction the model is trying to learn the distribution of the segmentations of the labels across the image. And so this is an example. These are what these different models that have heuristic ways of training and the loss functions do. So you see they fail in all kinds of different ways. And this is another variant. This is another paper that's very close to what we did here. And they both do a decent job at this task. So you see what is really nice here is that, as I said before, we have this grader here that is not sure if there's cancer at all, and the model, it knows that. It knows that there is a probability that there's no cancer at all, but it also knows that if there is a cancer, it must have some shape distribution, and this is really nice, and these things are coherent. The way we see that this is coherent is by trying to understand what the model is doing. Now, this is the nice thing. Is that because we trained this with a very low dimensional latent space, in here in this case is a 2-dimensional latent space. So the latent space learned some quite meaningful way of parameterizing the masks, the cancer shapes. So this is how it looks like. So this image is what the model would have generated if I pick a latent point everywhere in this image, and these circles indicate are the equiprobable lines of the prior. So this is just to give you an idea of the likelihood of this thing. So this is anything along a circle has the same probability under the prior of this model. And then we look, where do the graders live in the latent space of the model? And we see that it makes perfect sense what it does. For example, the grader number 0, it says there is a complicated mask, so they think there is a cancer there, and it has this big shape. And then if you look where it lives in the latent space, it lives in the region where the model would have generated a mask. So this makes sense. Grader number 1 thinks there is no cancer, and when you map to the latent space where they go, where he goes, where she goes, we know it's a she, that grade goes to the empty space. And if you observe what the model has learned, it basically has learned along one axis, it has learned to parameterize the size of the cancer region, and along the other axis, it learned to parameterize the shape somehow. And another thing that is very important is because this this model was trained in a principled way, it is also calibrated. So what this means is that if you have many different possible labelings that happens at different frequencies, let's say I have an image with a car, and there's 10% probability that car is a model A, and 10% probability of model A, and 90% probability of model B. I want the model to sample 10% of the time a car with the label A, and 90% of the time with the label B. I don't want it to sample with 50-50. That's not sufficient, because if you have a practitioner, a doctor looking at this data, they must have an idea of how certain the model is that each thing is happening. And this is another data, but is a similar type, so it's with a lot of ambiguities in the labels. And then we compare the true frequencies with the frequencies learned by the model. And you see this fairly calibrated. And if you do the same plots for this models trained with heuristic losses, you see some miserable failures in the calibration plot, like this. So if you want to do any like a real world application, this kind of calibration plot is really important, because we want to be sure that the frequencies coming out of the model are also correct, not that not just that what it is producing looks right. So we want that the frequencies look right too. So this is the first half. Okay, so thanks for coming back, everyone. Yeah, so let's start with the second part. So in this part, as I said, I will start by revising the stochastic approximation to compute the gradients in the variational approximation. The ideas are a bit more general than just the variational case. So you can apply these ideas to many other cases, and indeed people are using this same estimators to control problems and other applications beyond the generative models. Then I go to the thing I think is really important in latent models, which is this kind of approximation that I mentioned before. They are very simple. As I said, all these approximations here, they were made so that some human can compute by hand the posterior. So these approximations, they typically focus on the mode of the posterior. So if you have a multimodal distributions, they will tend to capture the highest mode, or the top n highest modes of the distribution. But if you have some complicated shape, if the posterior has some complicated shape, it is going to be really hard to learn the model with this type of approximation here. And that's why I started thinking about structured inference models. Of course, people have been thinking about this for a long time already, and there are lots of papers on this. But what is new and allows us to apply to lots of interesting problems is the combination of all these ideas of amortization, deep learning, to parameterize the maps inside the generative models with the structure, with extra structure that creates really complicated posterior approximators that we can scale and run on GPUs and everything. So that's the idea here, is to go beyond this like mode-seeking posterior approximation to structured inference. And then I will go through implicit models and what is a GAN, how it is defined and how we train it. I will explain different ways that people have used to train this type of model. And there is a study case here where I will go in detail in a model that does what's called the generalized moment matching method. And I will go step by step on how to train this type of implicit model. There's another use case here on the structured inference models, which I'll go through as well. And then we go through some very short mention about applications to RL, and we can discuss what's next. So I didn't say anything about how to compute the gradients of these divergences, or in particular the variational bound. So as I said before in the last slide, so we can view what's going on as some box that takes the joint distribution, the amortized posterior distribution, and it outputs a stochastic approximator of the gradient of the elbow or the variational bound with respect to all the parameters both in the inference model and in the generative model. As we also discussed, of course, we cannot never solve any of these expectations exactly unless we are doing some kind of trivial model, and we have to sample. So every time there's an expectation, it means that we're going to sample n samples from the data, n samples from the posterior, and average. So now let's think about the kind of computation we have to do. So the variational objective is something of this format. Like you have a function that depends on the latent variables. I've ignored the the x variable for now because we're focusing on the inference aspect. So we have some function of z, and I want to compute the gradient of this expectation. So I cannot simply put the gradient here because that is basically just wrong. First, is just wrong because the expectation has the dependency on phi itself, and I have to take that into account. So if you write the expectation explicitly, these are the two things that we have there. So the most naive estimator that we can write, which is the score function or likelihood ratio estimator, is where is it? Okay, yeah, it's here. And so the most naive gradient estimator you can write is this one. So this is called the likelihood ratio estimation or score method, because the gradient of likelihood of Q is called the score function. So this estimator is unbiased, and so this is always true regardless of what f is. So f can be non-differentiable, and as long as Q of phi is a differentiable function of phi, this formula is correct. So this formula you can use for any generative model. As you can imagine, as you can see, it doesn't make any assumption about z. So z doesn't have to be a continuous, smooth, can be discrete, can be anything you want. The problem is that exactly because it makes very little assumptions about f and about z and about q, the price you pay is that this is very high variance estimator. You can do some tricks that people do in practice called the contravariates to reduce the variance, but you cannot gain much with these tricks. So, but if you know more about what's going on, so you know f, you know z comes from some smooth distribution like a Gaussian, and you know q of z given phi, you can do better. What you can do is you can try to find some invertible function g, such that this is true. That a sample from Q from this distribution can, if you can find a function g such that a sample from Q of z can be expressed in this way as a function of some arbitrary noise. So, and p of epsilon is some source distribution, and the key thing is that so in general there are infinitely many ways you can do this, but the key thing is that to note that there is no phi in the base distribution. Phi only lives in G. So if you can find such a function, then you can build a really cheap gradient estimator, and this is what we call the pathwise derivative. So in the case of and this is what the first versions of the VAE use inside when Q is a Gaussian. This is really easy, because if Q of Z is a Gaussian, you can write a sample of the Gaussian as a mean plus the square root of a covariance matrix times a uniform noise, a spherical Gaussian noise. You can write a sample from any Gaussian as first sampling from a spherical Gaussian, then you multiply that by some matrix, and then you shift it by the same amount as the mean value. So in the case of Gaussian, this G function is really trivial to find. So if you can find this G function, now you have this. And we can rewrite this integral in terms of epsilon instead of z by just doing a change of variables inside the integral. And you can now rewrite this as this expectation. So now you have an expectation under epsilon, which is some arbitrary source of noise, and there is no phi anymore under the expectation. And the thing inside the integral, this f of z, now becomes f of z, which is some function g of epsilon and phi, and you can just put the integral inside, the gradient inside, because we are assuming that all these things are smooth and have finite integrals, so you can just put the gradient inside. And now this gradient estimator is really easy to implement if you know G. If G is just a known function, it's very easy to implement this gradient estimator. It is unbiased, and it can be estimated even with a single sample from epsilon. So now, in this derivation, I'm assuming that I can all I know is the gradient of f with respect to the parameters or with respect to z. But I cannot, if I am allowed to assume a little bit more, I can come with an even better estimator. So, so before going to that, it's just so in this transformation is a known trick. For example, in the case of a univariate distributions, you can explicitly build G. So G is the inverse of the CDF of the distribution. In the multivariate case, this is not easy, but the idea is the same. But what we do typically when you have a complicated distribution like this, in a multivariate case, we break the multivariate distribution as a product of univariate distributions conditioned on each other, and then for each univariate, then we can use the trick separately. So we can build a really complicated distribution and still have a very nice gradient estimator of that. And this is where you're going to exploit this massively in all the models that you follow. So now, let's look at the Gaussian case. So I have some function theta of z, and I have a Gaussian with the mean mu and the covariance matrix expressed in this squared form. We can explicitly write the transformation for this Gaussian, as I said before, the G that maps some arbitrary spherical Gaussian to this Gaussian is just mu plus C times the spherical noise. And if I plug this back there, I get a first order estimator of my gradient. It's first order because it only involves the first order derivatives of f. So this J is just the derivative of f with respect to z. But I can do slightly better in the Gaussian case because there's another formula that's true only for Gaussians. Now, this is not true if you have other distributions. This is only true for Gaussians. So this formula, you can apply it more broadly, but this one you can only derive in the Gaussian case, which is if you know the Hessian of the function f, you can use this gradient estimator. And you can prove that for broad family of functions, these will have lower variance than this. First, to start, if f is a quadratic function, the variance of this estimator is going to be 0. Whereas this will have is still going to have a variance. So the more we know about f, the better, the more we can reduce the variance. So this is a general thing. The more assumptions we make about Q and F, the more we can find ways of reducing the variance, because you can start incorporating this knowledge into how we estimate the gradients. So on practice, we don't use this estimator so much because the Hessian is still expensive to compute if you have a big deep generative model. But if you have something smaller, then this probably would be worth using as an estimator. Yes? Yeah, so, well, you have to track various numbers about the model. And you can see one effect of this being high variance is that if you look at the parameters, they'll be hovering around some region, but never going down. And if you can detect this kind of behavior, it is generally means that you have too much variance in your gradient. So it can never go down beyond a certain level. But this is a very empirical thing. So you have to track various numbers to detect this behavior. So one typical thing that we see, and this is very easy to do, is that if you start, let's say, with a fixed, fixed learning rate, and train a V, a E, or a draw, or any version of this model up to a point where it looks the loss is constant. At that point, if you half the learning rate, you see that the loss is going to jump down. And this is uniquely due to this noise. It's just there's so much noise that it cannot go down, but it is hovering around this valley. So this is the kind of effect you can see and somewhat control. That's why we unfortunately have to play with annealing learning rate schedules. Start with high and go slowly down. Unfortunately, we cannot avoid this if you want to find the best possible Q. And we can also try to track the signal to noise ratio of the gradients. We track the variance and its expectation in a batch, and we can have some heuristic that if that's beyond some number, then you do something to the learning rate or increase the batch size. There are some papers exploring this type of thing too, but in my practical experience, just reducing the learning rate seems to be the easiest way of go around this. But it's a very specific to every problem. You cannot use the same schedule for every problem. So just another point about the variance. You can prove that for certain classes of functions, the score method that I mentioned before will have lower variance than the reparameterized gradients. But these functions, they look really weird. These functions are functions that are bounded, but the gradient is not bounded. So imagine like some parabola that has a very small wiggle, like a quadratic function plus a cosinus with very high frequency cosinus. Then the gradients will be enormous at some points, but overall the function is well behaved. But the gradients have very large values because of this tiny wiggle. So if you make this frequency too high, then the variance of this will explode, of this gradient estimator. And the score method will have lower variance. But for any function that is smooth, you can prove that in terms of the, for example, for any polynomial function, the variance of these estimators, either one, is going to be smaller than the likelihood ratio method. For any kind of unbounded nonlinearity like ReLU or exponential, the variance of this estimator is going to be smaller. But if you have some cosinus, then you cannot prove anymore that the variance is always smaller, and because it is going to depend on the degree of smoothness of the function. So you have this trade-off to consider. So now beyond the mean field. So as I said, just to reiterate, mean field is just using a Gaussian posterior, basically. So that's the idea of mean field approximation. And the in the case of continuous variables, and in the mean field approximation was introduced in a discrete case. And to my knowledge, the first person that did the mean field approximation was Enrico Fermi. He was trying to calculate the distribution of electrons in a piece of copper. And he didn't know he was doing a variational approximation, but he made the approximation that the actual value of the number of electrons in some region must be equal to the average. And this is an approximation that he then used to calculate a set of fixed point equations that's called mean field equations, and that gives the expected number of electrons each in the whole piece of copper. But later, as we understand better what's going on, we can reinterpret what he did. So you have this distribution of number of electrons that's described by some generative model that assigns a probability to every possible configuration. And he introduced the variational approximation where all the values of this number of electrons, they're independent of each other everywhere. And when you do that, all the equations simplify because everybody is independent of each other. And you can compute the mean. And that's how the mean field appeared. But in the case of continuous Gaussians, the continuous distributions, the equivalent of the mean field is just approximating your posterior by a Gaussian, by a unimodal thing. Now, we've been trying a lot of things to get rid of mean field type of approximations, and one of the best kind of architectures we have is to create this autoregressive posterior distribution. So one of the best models we have in the sense is called the draw. It doesn't really matter why you call it the draw at the time, but the point is that it has both an autoregressive prior distribution and an autoregressive posterior distribution. So now, because of this autoregressivity in the latent space, it can model really complicated dependency among the latent variables. And moreover, this dependency happens at different spatial resolutions in draw. So we are thinking about modeling images. So as we have this multi-layered structure, so each layer is actually responsible for looking at modeling the image in a different resolution. So there are lots of other structures we have explored, and other people too, like more structural, even more structured priors and posteriors. And in this case, basically, this, in this case of this model, it really maps to the case of a render engine. Imagine that you have a render engine that takes as input a list of objects and their position and their color, and just draws it. That was this model. So this model, it has a very structured prior that specify what to draw, where, and some other properties, and it just generates this in a recurrent way. So it keeps sampling objects and their position, and then this just passed to some map that can somehow render that image. We can create, we've been using this structure in all kinds of other places. I will not go through the same supervised learning for now. So as I said, what we mean by mean field is that you have this complicated posterior, and we are trying to approximate it by something that doesn't look like the true posterior, but just a Gaussian. And mathematically, this means that we are modeling all the latent variables also as a product of independent distributions. This is also part of what makes the mean field distribution, is that it model all the latents as independent of each other, and on top of that, it assumes that each univariate distribution is a unimodal thing. So it's a very limited, is a very simplistic approximation of the shape of the true posterior. And when you train a VAE, even on a simple data set like MNIST, which is just handwritten digits, we see the consequence of that. So this is an experiment where we trained a VAE with only 2 latent variables on MNIST. So it only has a Z1 and Z2. So we can compute the true posterior of this VAE by just brute force, by computing the likelihood on every pixel in a grid up to a certain region. So we compute the true posterior by just brute force enumeration of all possible latent variables. And this is how it looks like. For many samples, they look like this. So I'm going to show a few more. But the point is, on one side, it's good that it looks like a concentrated blob. It's not like some really complicated multimodal thing, at least not here, but we do see multimodal ones. And this blue thing is what the posterior, the inference network is trying to do. So this is, the blue thing is what it is the best it could do in approximating this true posterior here. You see that it makes all kinds of mistakes. So first the mean is slightly off, it's slightly bigger, and here is a bit worse. The mean is off, the size is off, and is a bit tilted. So this model, even though it's been trained with unbiased gradients and in an unbiased way, you can still see that after a lot of training, there is still some bias. And this bias that we see there, in a recent paper, some people introduced the term amortization gap, because this gap can be interpreted as a form of underfitting of the inference network to the true posterior. Because this case, it could do a very good job here approximating this shape, this density, but it doesn't. Now, as you inspect many more samples of the true posterior, then you can see cases where Gaussian is not a good approximation. So first of all, some posteriors have a slope. So if your Q cannot approximate a tilted Gaussian, for example, which is the case if you use a diagonal Gaussian as your posterior network, it cannot approximate this type of a shape, for example. So these green dots here, they are just the samples from the prior. So this is the green stuff, is the prior. So it gives you an idea of how concentrated the posterior is relative to the prior of this model. And here's the prior, the green, and the posterior is a tiny blob there. And if you keep zooming, so these are different zoom levels of the posterior. So this is looking at 3 standard deviations of the prior. This is looking at 1, and this is keep zooming and so on. You see that as you zoom, you started to see the non-Gaussianity of the true posteriors. You see they have some structure there, and in some of them, this structure is highly non-Gaussian. It deviates substantially from a Gaussian. like this type of thing, or even this, or that is kind of a triangular shape with this high density in the tip and a long tail. As you know, the Gaussian doesn't have a very long tail, so it is going to do a really poor job at approximating this. So visually, it looks like it's doing a decent job, but just think, the Gaussian is elongated like this. It means that it's putting most of its mass around here, but this shape has most of the mass there. But the Gaussian cannot approximate that shape, so it must find some kind of compromise at being between putting the mean of the Gaussian somewhere along this shape and capturing the mass. So you can see that there is a lot to be gained if you could have a better posterior. And then just to iterate even more, so on one extreme we have the mean field approximation where everybody is independent and just Gaussian. In the extreme case, if you could compute the true posterior, in the true posterior everything would depend on everything and it would be very complicated. And but now we can start adding some structure to the posterior and see how far we can go. So one way of introducing structure is through adding the first thing you can do is to first add the covariance matrix, right? The vanilla VAE, if you have seen it implemented, is just a diagonal Gaussian posterior. So that's a really bad approximation. And then the first thing we can consider is okay, we are using diagonal Gaussian. Next step is a full covariance Gaussian or a low rank Gaussian, and that's what people have tried here. You can consider a mixture of Gaussians too. So none of these ideas have gained much. In very high dimensions, going from a diagonal Gaussian to a full covariance Gaussian doesn't buy you much, because the density is not the most of the relations is not in the how things are correlated, but in the complicated shape of the posterior. And if you have a mixture model, it's really hard to train a mixture posterior jointly with the rest of the model. First, it is very expensive because for every component in the mixture, you have to compute the reconstruction term independently. So as you grow the number of components in the mixture, your algorithm gets more and more expensive. There are some approximations to that that increase the variance at the expense of less compute. But on practice, the result is that we cannot really go very far with this idea. There is some interesting family of ideas that also that work quite well, which is the idea of introducing a auxiliary variable. The idea is as follows: you have this VAE like this, it generates Z and will go to X, and you will create this this dummy variable W that has this particular dependency graph. You see that W is unobserved, so if I can because of this graph, because of this direct dependency on Z and X like this, I can just integrate it out, and if I integrate W out, I get back the original VAE. But when I build the inference model, I can build it this way. I can from X, I create some Q of W given X, and then given X and W, I generate a Z. So you can show that this allows you to approximate much more complicated posteriors. And people also have tried more traditional like copula methods, but copula methods are basically limited by the copula function, and there are not many copula functions in very high dimensions that you can use. So it's kind of a dead end as a way of creating a complicated posterior. And the other idea that we have been exploring, which is very promising, and since we proposed it, we made enormous progress in the and by we I mean the machine learning community, is this idea that we start with a null but simple distribution like a Gaussian or uniform, and then we pass it through to a series of transformations such that at every step it becomes more complicated. That's the idea of the normalizing flow. So more specifically, this is the idea. So we start, let's say, with a 0-1 Gaussian, and then we apply a transformation, and then every step, this transformation adds more parameters. And then by the end, we have something very complicated. And as long as every time the transformation f is smooth and invertible, we know the exact formula for computing the likelihood at each step, which is just this standard formula from change of coordinates in a distribution. So if you do this a number of times, k times, and then a sample from this posterior is just like the original sample is 0 from the 0-1 Gaussian that you pass through a series of functions, and then the likelihood of that sample under this model or under the flow is just the likelihood of the original sample plus some correction, which is the log likelihood of this determinant of the Jacobian. So as you can imagine, the critical thing for this idea to work is this term. So we must find f's such that we can compute this efficiently. So that's the contribution of the normalizing flows together with deep learning. It's not just to use this formula. Everybody knows this formula. But the point is, how can we compute this in a reasonable amount of time? So that's where the contribution comes. So one simple family of normalizing flows we call the planar normalizing flows. And you can understand, even before I show you the formula, you can easily understand what it does to a density. So the planar normalizing flows, let's say we start from a 0-1 Gaussian, that's the Gaussian. And then if I do one step, all that it can do is to pick a plane, and it can either contract or dilate the density around that plane. So in this case, the plane is this horizontal line, and it contracted the density along the vertical line. So it created this squeeze the Gaussian. But by applying the same flow in the orthogonal axis, I can now create a multimodal distribution. So I can transform a Gaussian, univariate, unimodal Gaussian into a multimodal thing. And if I keep doing this, I can create as many modes as I want. And not only that, if I really wanted, I can analytically compute the position of each mode. Yes? Yeah, the idea is that you basically, all you need is to pull away from a plane. And like you choose this plane, vertical, and you pull the density away from the plane. Because the plane is passing through the peak of the Gaussian, through the mode of the Gaussian, you're gonna create two regions of high density away from the mode. And this is a similar thing that maybe you can visualize better what happens if you start from a uniform. So this is the uniform distribution in the box. That's the initial sample. And this is a random transformation. So it picks this line and pulls the density away from the line. So it creates a hole in the density. And if I combine multiple of them, I can create these regions of higher density and the regions of lower density. And I can, by using many of these, I can create some complicated posterior. Yeah, so the scaling down happens automatically because these are probability distributions, so they are they are normalized. So whatever you do, the integral of this must be 1. So this is what these two things combined is what allow us to create a multimodality from a unimodal thing. So this is just to illustrate that we can create a very complicated density by applying a sequence of simple transformations to a simple distribution like a Gaussian or a uniform. Yes? Yes, yeah. Yeah, exactly. The idea is that so each transformation will have a bunch of parameters. Like in this case, because it's very simple, the parameters is basically where this hyperplane lives, and it's a slope, and how much you want to pull away or towards the plane. So you have a small number of free parameters for each flow, and then because they are very simple, you have to stack lots of them. So you pay some computational cost on this side. But this will this limitation is addressed by new families of flows that people have been working on that I will also explain. So now on practice, now if we now optimize the parameters of this flow, in the previous slide I just used it random parameters just to convince you that you can create a complicated density. Now the question is, can I learn a complicated density? And this is what this plot is showing. So this is the true posterior. Imagine that this is my true posterior. So if your variational posterior is just a Gaussian, you are doomed. There's nothing you can do there. If this is how your true posterior looks like, and you're trying to approximate this by a Gaussian, what is going to happen is that it's gonna move to one of these modes, and it's going to form a tiny Gaussian inside this bean shape. So it's going to be a really bad approximation. But with this planar flow, if I learn the slopes and how much I pull away and towards the plane, as I grow the number, I can get closer and closer until it gets really close to the true distribution. And this is just to illustrate many other behaviors that are very non-Gaussian. For example, there's nothing you can do if your true posterior looks like this and you're trying to approximate it by a Gaussian. Same here, same thing here and there, and you can approximate it this way. So, but this type of flow is still too simple. If you have now, imagine that you have some 1,000-dimensional latent space that is trying to explain some images. This is not going to work very well. Okay, yeah, just now we have to come back and think again about what kind of transformations can we really do in this setup. So the transformation that I showed you is what we call planar flow, that it looks like a tiny residual network that has a single hidden layer. So you can create this planar contraction or dilation by creating a MLP that has a single hidden neuron. So it's very weak. That's why you have to stack lots of them. But then a really cool idea came from this paper called the real NVP. And the name doesn't really matter so much, but what the name means is the real non-volume preserving network. And the real is because it's operating real numbers. The idea of this map is very simple, but it's very flexible and allow us to do a really complicated flows. I'll expand this flow a bit more. Another type of flow that was introduced just after is called inverse autoregressive flow. The inverse autoregressive flow is basically built from the realization that if you build an autoregressive distribution and invert it, you can forward the inverse much faster than you can forward the original map. And this happens because, so if you build an autoregressive distribution, you have to sample the latent variables sequentially. But they realized in this paper that if you do the inverse map, you can sample all the latent variables in parallel and just parallelize the map. So that was the key insight of this paper. And in terms of flexibility, you don't gain much compared to this. So that's why I will now expand this idea a bit more. Okay, before going to the MVP, you can do something really cool with this idea too, is that if you can embed any manifold in Rn, you can build a density on it, just almost trivially. You can transform any density in Rn into density in the manifold by just by just applying your embedding map from R to the manifold. So of course you must know this map. And as long as you know how to compute the metric on this manifold, which you should know if you know the map, all you need to know is this determinant of the metric, the log determinant of the metric, which you can compute for any kind of products of spheres and torus type of surface. You can compute relatively cheaply. So you can build now, so imagine that you're trying to model, for example, some robot arm that is parameterized by the joint angles. So joint angles don't live in Rn. Joint angles live in a space that is a product of torus. And if you want to put a density there, it's really hard. It's really hard. There's very few papers exploring complex density in arbitrary Riemannian manifolds, just because there's no systematic way of building complicated densities there. So you can have like a kernel method and a generalized kernels to arbitrary manifolds, but it's computationally very expensive, even more expensive than it is already is in Rn, because the way that you generalize the kernels is that a kernel is simply a function that depends on the distance between 2 points. When you go from Rn to the manifold, the distance becomes what we call the geodesic distance, which is the short distance within the manifold between the 2 points. And unless your manifold is a sphere or torus, the geodesic distance is really expensive to compute. So there are really no easy ways of doing this. But if you know these maps, we can just use the machinery of normalizing flows in Rn and just pull them to an arbitrary manifold, and which is may have some really interesting applications for modeling any kind of angular data or periodic data, for example, or data that lives in hard constraints. Even if you model the robot arm by the positions, these positions of the joints live in a very constrained surface, and it doesn't make sense to just put a Gaussian on Rn for the positions of the joints, because then it means that the length of the arm of the robot will be stretching according to samples, etc. So if you want to incorporate hard constraints, this is one very easy mechanism that you can consider. So these examples that we did, we built a Gaussian mixture in Rn, and we can easily put a Gaussian mixture in a sphere, torus, and a cylinder with this trick. Yeah, so and just to summarize these structural posteriors before I go to a case study. So we've seen different mechanisms for building these normalizing flows, for building structured posteriors. One is to try to directly model it, but in general it's very expensive. You can do autoregressive models in various ways, auxiliary variables, mixtures, and the flows. And to the best of my knowledge, from all these methods, the flow normalizing flow ID is the most scalable way of doing this, and also from an optimization perspective, it's very convenient. Now, I would like to go in more details through one particular model that actually puts almost all the things I presented up to now together. So this model is a VAE type of model, but it has a structured prior, structured posterior, and we use it to do data completion, quantify uncertainty, and representation learning. So that's why I would like to go in more details in the inner details of this model. So the motivation, one of the motivations for building this model was to try to understand a three-dimensional scene. So, and the thing that we first thought was, okay, I should be able to form a three-dimensional model of a scene if I can see it from multiple points of view, points of views. And if I know the orientation of the cameras, there are handcrafted algorithms that can do this for simple scenes, and they work very well. So we wanted to learn it, but we want to learn it in a very particular way. We want to first encode the scene into a vector of fixed length, regardless of the number of views we have. And this vector should encode everything about that scene, including the uncertainty of the unobserved parts. And from that representation, we should be able to condition a generative model that has latent variables to produce an arbitrary view from a particular camera that is given. So the key insight of this architecture is that when you build this representation R, the network that produces this vector R, what you call the scene representation, it doesn't know yet which angle you're going to ask the generative model to generate. So it cannot specialize to produce the image from a particular direction. It must somehow encode the entire scene so that the generative model can later on generate every possible frame from that scene. So if you were to pass this vector to this network, it could just cheat in various ways. It could do some kind of lookup table where it looks from the views that were given, what is the nearest camera from the camera that I passed, and just use that to predict. And we have some experiments where it does almost exactly that. But so this is just an illustration of what happens. So we have one view. We move the camera, collect another view. We pass to this encoding network. And then we form this representation that is agnostic to the camera that we're going to ask it to generate. And and only later on, when it actually produces the image, it is informed about the direction that you want it to generate. So it's forced to encode all the objects somehow into this fixed length vector. So mathematically, this model can be written like this. So it looks very complicated, but it is 20 lines of TensorFlow. So you have this scene encoder vector that is permutation invariant. So it takes all the views and all the cameras together and forms a permutation invariant representation of the scene. Permutation invariant with respect to the order of the frame. So it doesn't really matter if I see this first and that, or that and this first in a scene. As long as there's nothing moving in the scene, it should be the same. Then the rest of the model is basically an RNN that is building a autoregressive distribution. So you don't have to follow all the symbols. The most important thing to follow is just that you have this prior. So there is a state variable h, and at each step we read the current h, map to the sufficient statistics of the prior, sample it, and that sample is used to go to the next step. So each step is conditioned on the priors on the latents that have been sampled before. So that forms an autoregressive prior distribution. And at the end, after running this for a number of steps, we take the last state of this RNN, and that is what is used to generate the image. And this is the loss. This is the variational bound applied to this model. So you have the same terms as showed before, but with a bit more detail. You have a reconstruction term and the KL term, which is the regularization term. And because it's an autoregressive model that has n layers of latent variables, you have one KL term per layer. And this is how the inference network looks like. It's pretty much the same thing, with one difference. One key difference is that you see in this list of inputs to this transition map, there's no X, right? The prior of the model is not allowed to look at the thing it's going to generate in advance. Otherwise, you couldn't be able to produce any sample. But the posterior network is allowed to look at the target. So that's the difference. It can see the image that is going to generate. Yeah, so So V is the camera, so I didn't want to go explain all the symbols. So R is the scene vector, and VQ is the camera I'm asking it to generate. And the important point of this RNN here, that the only thing I wanted to draw attention to is the fact that there's no X here. So X is the image that they're generating. The point is that this is an RNN that is just updating its state and sampling the latents and repeating the process, but it doesn't know X. And only then it can generate some X. But the inference network, it knows X. So it is going to form a autoregressive distribution of each layer of latent variables conditioned on the previous latent variables and on the image. And even though this model is defining some really complicated density, with all these tricks that we have discussed before, it's really easy to train this model, because we can just keep stacking layers and backprop through them by injecting noise at the right places. And this is just repeating the same loss. Oops, again, the loss. So this is what happens when we have a almost fully observed setting where the model can see almost everything from a single image. Then it can easily generate the scene from multiple viewpoints, and there's no uncertainty in this scene, even though it's coming from a single image. And so, but what happens when there's a lot of occlusion? So when there's a lot of occlusion, the model is very uncertain. So as I showed before, from a small number of views, it doesn't know the layout, but as it keeps walking around and taking more pictures, the layouts, they match more and more the truth. And this is what the model can imagine. So after taking these 4 pictures, we can walk around on the model representation of the environment as if it was the real environment. So in this particular environment, it is particularly good, but this environment is quite simple. So here is the same thing. Is from this picture, once you given this single picture, you can navigate through the three-dimensional representation that the model has formed. And we've been trying in various ways to understand what the model really understands about the scene. And by doing various imputation experiments, we can demonstrate that objects are somewhat factorized in this scene representation vector. And the things like the position of the light in the environment can be extracted from that vector too. So there's quite a lot of factorization that happens naturally, just because that's the only way it can to explain the scene. And as I explained before, you have this this model allows us to, because it's a generative model, and in particular it's a latent variable model, it allows us to quantify the uncertainty of a new prediction by looking at, so this what we call surprise is what we call the predicted information gain, which is in this case is just the average of the KL divergence term. So the KL divergence term is the predicted information gain, and its interpretation of this number is that how many bits do I gain by observing this frame, given that I already know up to this frame. So given that I know nothing, this is the number of bits I gain by observing this frame. And given that I already know this frame, which is completely informative, I still gain about the same number of bits. But given that I know something that's actually correlated to what I'm observing, the number of bits that I gain is much lower now. And so on and so forth. At some point, you gain zero bits because you have seen the whole scene. And if you average across many scenes, you can compute this average of number of bits as a function of number of views. So what this plot shows is that how many bits do you gain by observing a random view from a scene, given that you already have seen this many views. So you can You can put precise numbers on surprise and uncertainty. And another application that I didn't mention before is the idea of representation learning. So this scene vector, it must represent the scene in a fixed, it represents the scene in a fixed length way, and in a somewhat, the objects are there in a somewhat factorized way. So it should be useful to do some spatial control task, and that's what we did here. So we trained the model in the same way to look at this Jaco arm, robot arm, and the task of this arm is just to touch the object. So we pre-trained the model, and now we did the following experiment. There is a camera attached to the hand of the object, so as the robot moves around, the camera moves together. And we train a policy network just to take the vision of that is attached to the body of the robot and tries to solve the task, which is to move the arm towards the object. So if we fix the camera position, there's a difference. So if you fix the camera position, so actually the camera is not on the arm, but is floating around at a fixed position. The model from the raw pixels, it eventually learns to solve the task. So it can solve it, but it just take a long time. But if instead of the raw vision, we feed the scene vector learned by the model, it learns much faster to solve the same task. So it means that this representation is really useful for this kind of spatial task, or at least for this particular task. But now there's a case where the policy, the agent that looks at the raw pixels completely fails and it cannot solve at all, which is the case where the camera moves. So when the camera is moving, the agent that is trying to solve the task by just looking at the image directly completely fails to solve the task, at least up to 30 million epochs of training. Whereas the agent that is looking at the scene vector, it still solves the task in about the same time. It still takes a bit longer, but it can solve it. And if you look at the scene vector in both cases, it's the main thing that's going on there is that it's quite stable, because it represents the scene, not a particular view. And the scene is always the same, regardless of whether the camera moves around or not. So it's a much more stable representation. This representation is learned in a way that is completely unaware of the reinforcement learning aspect. So it's just a pure generative model that is trying to compress the scene. That's what the model did. Okay, so yes? Yeah, so Z is very, very large because of the type of model. Z is about 10 times larger than the image in this model. So there's a lot of Z's. But R is tiny. I think for this task, R was something like 16-dimensional or 32-dimensional vector. So R is very small vector, but in this for this particular model, Z is very large model because of the autoregressive step. At every step, it generates more latent variables. Yeah, so implicit models. So as I said before, so completely changing the topic. So if you have questions about the other types of models, you can ask now, or I can try to come back after. The idea, as I said, an implicit model is just a model that you don't know, I mean, that you cannot compute with the same techniques as before P of X, because it is defined in a way that that X is a deterministic function of Z. And of course, the goal is still that if you have some target density, you still have to want to come up with an algorithm that will change the parameters of F such that the X's that are coming from this model will approach that density. So the first step is, as we discussed, is to come up with a divergence. So that's the principle. And then once we have chosen a divergence, we have to come up with how to approximate it and compute its gradient. And this is what all these papers, GAN papers, are about. Is about different divergences, different estimators of the divergences, and they vary in different degrees of how much heuristics you put there, or how much human knowledge you want to put into the estimation. So one of the ways that you can see this is that so this is just telling us about different divergences. So we have this called MMD divergence, max mean discrepancy. We have moment matching, and these are all different families of divergences. It doesn't really matter which the details of them, but they're all different ways of comparing two distributions. And all of this, if you had infinite capacity, an infinitely ideal optimizer, all of these densities should be able to bring the density to the target density. But of course, in practice, all of this is extremely approximated, and the optimizer is not perfect. So we have to cope with the imprecision. So for a certain number of these divergences, there is a key quantity that appears, which is a probability ratio. So these probability ratios appears in many of the formulations of GANs, and so it makes people think that okay, this is how can we estimate directly a probability ratio without having to compute the individual probability first and take the ratio? Can I directly compute the ratio? So in an ideal world, there is a very nice answer to this, which is exactly what a GAN does. So let's say I want to compute this. So I have a density P star, and I have a density Q of X. I want to compute the ratio. What I can do is, let's say I now produce a bunch of samples from P star and a bunch of samples of Q, and I create a dummy label that is, let's say, 1 if it came from Q and -1 if it came from P. So I create a data set like this, and this Y is the label. And by his rule, we can compute the P of X given a label by just inverting this. So basically, P of X is one of these two densities. P of Y is the probability of is the marginal probability of picking one of the labels, and this is the label of a particular image. So now let's think about this object, P of Y given X. So P of Y given X is just a classifier, right? P of Y given X is I'm classifying whether the image X came from Q or came from P. So this thing we can learn with traditional deep learning techniques. It's just classification. It's a convnet that outputs a probability. We can do that. But then you can use this. As I said, you can build this data set, and you can use this classifier to now compute the two distributions and approximate their ratio directly. So now the ratio is only a function of the classifier. So if I have trained this classifier, I can compute the probability ratio by just a very basic manipulation. Of course, this whole thing is assuming that the distribution P of Y given X is the true distribution. This formula only makes sense if I make this assumption. But that's quite an interesting trick, because each of these distributions is a really complicated object, right? It's a distribution over images, let's say. Each one of them is a very complicated distribution of images. And this thing is just a classifier. It's just a thing that puts a separating boundary between the two densities. And we can compute this ratio is just the ratio of the class probability. So this is quite interesting idea. And then basically, once you have this observation, now everywhere you have a probability ratio which appears in many divergences. All the F divergences, KL divergences, many divergences can be written in terms of probability ratios. So you can just replace this by this formula, and the price you pay is that you have to train a separated classifier. And that's what is called the discriminator network in a GAN, in an implicit model. So another way of looking at it is that you're using purely supervised learning to do something that is unsupervised. Like there are no labels about the images. You're trying to learn the density of the image, but through this machinery of learning a discriminating function, you can now build the loss of the generative model. So that's quite a neat trick. It relies on lots of assumptions, but a lot of anything you would do, you need assumptions. There's no way to avoid it. So just to give an example of how these things look like, the generator is not very different from a VA generator. It's just a convnet that takes, or some arbitrary map that takes your latent variables and maps to an image. That's the generator. The only difference between this and a VA is that if you were building a VA, the generator would output the sufficient statistics of some distribution that you're going to parameterize at the bottom, at the pixel level. And whereas here, what comes out of G is the image. Then you build this loss using the discriminator, which is just a convnet that takes the image and outputs this scalar number D. And you solve this problem. So D is the discriminator. It's trying to classify whether an image came from the model or from the real world. And the parameters of the model, you're just trying to minimize this the same F. So as this approach of trying to learn the density is computationally quite different from the VAE case, because the VAE you're trying to find a minimum, a global minimum or global maximum of something, whereas here you're not trying to find the minimum, you're trying to find the saddle point, which is this mean with the max, right? This optimization is going to find a saddle point of this function. So from a pure optimization perspective, this is much harder. That's why there's a lot of issues with the convergence in using this approach, and there is really a huge number of papers trying to mitigate that. So this is just to give some more ideas of how the gradients look like with respect to the parameters of the discriminator and with respect to the generative loss. So if you look at these two things together, basically this is like the entropy of the discriminator, right? It's a log. So if D is the probability of being in one class, this log D plus log of 1 minus D this is the entropy of the discriminator. So you can interpret what the generator is trying to do is the generator is trying to generate an image such that the discriminator has maximum entropy, which is the case where the discriminator will say, I don't know what's the class of this image. It can be 50% from the model or 50% from the data. So this is what the generator is trying to do, while the discriminator is trying to do its best to separate the two images. So this is a small scale example of something like this, the optimization of this process happening. So this yellow line is what the discrimination surface. So everything that is on one side of this line belongs to one class, and everything that's to the other side of the yellow line belongs to the other class. Whereas the density learned by the generative model that is trying to fool this discriminator is the red thing. So in low dimensions, this converges. And this particular case was actually not using a classifier. It was using this this slightly more general idea, which is the idea of generalized moment matching idea, which is which is just really just another divergence. So the idea of this divergence is that we choose a family of functions, and then we compare the moments of this function under the data and under the model. And of course, the model is trying to make the moments, its own moments, to match the moments of the real data. So you compute the moments of f with respect to the model and with respect to the true data, and you try to minimize this. But you choose inside the family of f's that you have decided to use, you always pick the worst one. That is, what is the f that maximally discriminates the moments of the data and of my generative model? And that's what this loss is trying to do. It's trying to pick, I want to minimize the worst possible scenario of separating the two models. And this f is implemented by a convnet, as you can imagine. And then there are some conditions on f that corresponds to different divergences, but these are the differences that we get. So of course, there is enormous literature in mixing the two, VAs and GAN hybrids, and every possible permutation of loss terms you can imagine has already been tried. And most of them are very heuristic, and some of them are somewhat principled, and some of them we don't even know what's going on. But there's some sense in this in these searches. What is really interesting about having these two families of models is that it really created this really rich search of where is the right kind of combination of principles in terms of divergence, but also optimization, and also linking to the architecture of the model. So it was really, I think, healthy for the community to have this kind of competing approaches. And as you can see here, they're not competing, they're just being merged in various ways. And related to that, I would like to go to do another case study, which is based on this paper, Learning Implicit Generative Models with the Method of Learning the Moments. Oops. So again, this method is all this divergence is we call integral probability matrix, is just a particular case of this family of divergences, but we also call it a generalized moment matching, because you can imagine the original moment matching is just matching things like mean, variance, kurtosis, etc. of low dimensional distributions. But we want to write it in a way that is scalable. So we want this f to be very high dimensional. So in the model they propose in this paper, as in any implicit model, you have some generator network. It doesn't really matter what are the details inside. All that matters is that it takes some latent variables on the top and outputs an image, and it's a differentiable thing. Now, the main issue with the method of moments is that you can prove mathematically that if the number of moments is smaller than the number of parameters, you'll not be able to recover the parameters, right? So imagine that you have 100 parameters, and each moment is a one scalar equation, like the average of something of a scalar number under both the data and the model must match. So each moment constraint eliminates 1 degree of freedom. So if you have lots of parameters, you're going to need lots of moments. So you cannot keep inventing moments by hand like you can do in a univariate density. You need some automated way to specify the moments. You can just build feature vectors, for example, which encodes the activation of the layers, and the gradients along the layers and the value of the image, and consider all of this as my list of moments. And the idea is that now we're going to learn as much as we can from that list. So as before, you had this discriminating loss, which is basically another way of rewriting the generative objective. And generalized moment matching loss is this R function here. So basically what the moment function is trying to do, it's trying to reduce the variance of the gradient. That's what this loss is doing. So if you use this loss to learn your moments, so this is trying to find the most distinctive features that will maximally disambiguate from one data from the other, because that's how you can reduce the variance of the moments. Now the generator objective is just to match the two moments. So it's the mean square error between the moments calculated with the model and with the data, and is the real data. And the one challenge here is that this average must be taken over the whole training set, and so you have again the same kind of thing we saw before. We have a nonlinear function of some expectation, so this has a biased gradient. But in this particular case, because this nonlinear function is just a quadratic, we can remove the bias if you want. So this is how the algorithm looks like. We have to first optimize the moments. We have to find the set of moments. So we have to solve this inner optimization that optimizes the most discriminative moments. And then given that, we compute we actually compute the moments over the data and over the model, and then we optimize the generator to make these moments a match. So this is how the algorithm looks like. And this is kind of what this kind of model does. So this is how the data looks like. This is the CFR10 data set. So if you use random features, so if you use just compute moments from a randomly initialized convenant, it doesn't really work. This is what it learns. So this is really to demonstrate that you have to learn the moments. So if you don't learn the moments is in a way that is specialized to the problem or to the data, you never gonna get even close to the density of how the data looks like. But if you use this algorithm, you get much more realistic images. So this is just another data set. It's the same thing with the random features and the learned moments. And this is a data set where it completely fails if you use the random moments. Maybe if you keep initializing it and retraining eventually to learn something, but this is what it did there. As you can see, this model is not perfect, but it is a very interesting idea. And this idea can be applied both to any latent variable models. It doesn't have to be applied to implicit model. We can train a VAE, what we would call a VAE, in this way. And this algorithm also works if the latent variables are discrete, because it doesn't assume that you want to backpropagate through the latent variables like we do in amortized inference. So it has these nice properties. So there is still a lot of work needed to scale this type of idea because of this limitation of moments that they must constrain the density enough to compare to the number of parameters. So as you keep growing the size of the model, you have to keep growing also the number of moments you're going to use. So I just wanted to mention a few points about generative models and RL, but just very quick points. One is that you can write RL as an inference problem. RL people don't like that, but that's just a mathematical fact. Because you can interpret the return as some unnormalized likelihood. You just say that the return I've got by taking some action in some state is some unnormalized likelihood function of that is modeling some dummy variable. Let's say the probability of success in that environment. then we can write a objective function for the now A is the latent variable, which is in this case it's the action. So we can write this objective function which looks exactly like the variational bound, the elbow. The only difference is that this R thing is not really a reconstruction likelihood, but it is just this unnormalized likelihood that has the return inside. Then you can interpret this as the policy having a prior over actions, and the policy that you actually use in the environment is actually the posterior over actions. So you can imagine having some prior, for example, a typical thing in continuous controls domain is to add some kind of entropy penalty, because you don't want your policy to prematurely converge to a delta, so you add some penalty. So this penalty turns out that is just the KL between your current policy and some prior policy. And if you put this penalty together with the reconstruction term, that's what we get, basically at the elbow of some kind of some generative model, which looks like this. And then in the same way as we do in the MVA, you can just compute the posterior, and if the actions are continuous, you can just do the reparameterization or the pathwise derivative. But if the actions are discrete, we have to use the likelihood ratio or the score function method that we have seen before. And this is just a lower variance version of that. So just by doing this, we don't gain much insight into the RL problem. We're just rewriting it in a different way. It's exactly the same problem that we're trying to solve before. But the power of this making this bridge is that there is enormous amount of machinery on the inference side of the story that we can now bring to reinforcement learning. And there's a lot of papers that use this idea to do all kinds of inference algorithms in reinforcement learning, like message passing and all kinds of variational approximations, MCMC, Monte Carlo, etc. And so this is just a slide that you've seen before. It's just this idea that the generative models can, not always, but they can learn useful representations just because if you train them in a way that is compatible with the task, the family of tasks you want to solve, you may learn some useful representations. But this is a whole topic on its own, and in general, it's not easy to know in advance how you should have trained your generative model to get the representations that would be useful for the task. So this is an open problem. Okay, so the future. So just a small recap. So you've seen lots of applications, this merge, you've seen the slides. All kinds of generative models, autoregressive, latent variable, implicit flows. We've seen some problems. How do we do the stochastic approximation, and how do we learn in implicit models? Now there's lots of open problems. So we're still trying to scale these things. So up to a couple of years ago, doing something at large scale was to train on CFR10. Now large scale is to be able to train these things on a much bigger data set like ImageNet. And the notion of scalability keeps getting keeps moving forward. As you improve, it also moves forward with you. So you never get there. The compute power we have now is thousands of times more than when you started, and it's still not there. So we don't know if we ever end the scalability limitations. But another point that I think that most of the things in this table are now about thinking about how to use the models, not just trying to make bigger and bigger images, but how to use them and use in a way that is meaningful to a task. Like how can I make a robot or a drone or some agent use these generative models in a meaningful way. So, and I think there are many aspects that we are still not looking too much, which is multiple data modalities, like a robot or an animal has at any moment in time a huge stream of data for many sensory modalities. We have accelerometer, proprioception, vision, auditory data, tactile data, smell data, and probably lots of other physiological data together with that our brains somehow processing in real time. But these models, they only look at one image at a time. That's all they're doing. They don't have a notion of persistence, don't have a notion of multiple different types of data. So of course, we can extend this to some extent, but I think there should be much more effort to train these models in a scenario that is relevant for agents and RL. So evaluation is still a lot of issues there. We don't know how to evaluate these models in the sense that there's no consensus on which metric we should use to rank the models. And the only thing people can agree is that you should always look at some task and evaluate how the model is being helpful in that task. At least there's no disagreement on the usefulness factor. But you're still not going to agree whether the model has learned the density of the data or not, or something else about the data. But at least you cannot dispute whether it's useful or not for your problem. Learning conditional models is still really hard. And as you have seen before, lots of effort in the most papers is just unconditional models, like just sample faces in the wild, or just sample random ImageNet samples. But to actually use these models, you must condition on something. The something can be the past, can be some sensory data, some task parameter. And the problem is that if this conditioning variables are complicated, pretty much all these models, they will fail in one way or another. It doesn't really matter if it's a VE or Pixel CNN or a GAN. It is really tricky to learn this conditional distribution. So in the particular case of GANs, you have this issue of node collapse. There's also issue of calibration. Parameter uncertainty is being completely ignored for now, just because it's too hard and nobody wants to even try. Or we have tried, but we just gave up. And other principles like this idea of likelihood-free inference that some recent papers have put forward. So these are examples of GAN failures. So and now I think there is what to me is the most important next step forward is you're not going to learn the causality of how an image was generated by looking at images only. So if you see a million static images, you're not going to learn what is an apple or how the shape of an apple combined with the rays of light to produce the image that you see. So the true causal process behind the image is not the image. You can only access that by doing some experiment that is outside the realms of image. You have to go there and take the object and look it around. And then you understand what's an object. So I think one of the next big things that we should look at, and there is indeed some people already thinking this way, is that we should really think of these models as embedded into embodied agents. So these agents will have lots of sensory modalities. But not just that. These agents, they take decisions that will influence the model and vice versa. So if I cannot disambiguate between the multiple causal explanations of the data, now because this model is inside an agent that can take actions, now the agent can formulate a plan to conduct an experiment in this environment or in the real world that you disambiguate between the models. That's exactly how we do science. We come up with a bunch of models and we design experiments to disambiguate among them, and then we just throw away the ones that are too far away from the data, keep the ones that are closer, and keep refining this loop. Or just keep all of them around with different weights, which would be the Bayesian way. So this is one idea like that is really what I think we should aim, but it's a really ambitious goal. So from these guys, what they propose, so these people, they look at CERN and they are proposing an automated physicist, which would be some kind of model of the particle physics that they use to compute lots of experiment proposals and ranks them according to expected information gain. And then it actually conducts the experiment at the machine and refines the model and keeps doing so on and so forth. So we can think about something like this in many different scales. Like you can imagine a tiny agent that conduct an experiment may correspond to simply just looking behind the screen. Like I cannot see behind this screen, so there are many things that could be behind it, and because I know that, I can plan and take a decision that will resolve this ambiguity. So I think this is one big step that we should pay more attention to. That's it.